Hi everybody, Miss Humphrey here. We're going to go through pages 14 and 15 on this next video. I have a pretty basic cell phone holder that I'm using for taking notes, and it like tipped over right as I was taking in the middle of these notes. So I had to start this one over. Unfortunately, there's a little bit of labeling on it, but that's okay. So page 14, there isn't actually a lot of notes to take right here. We're just going to look at some of the stuff on page 14 together. Now, one of the things that I want to make sure we know is that we're going to be doing a lot of unit conversions. You might recall this being called factor labeling last year in chemistry. And when you did it in chemistry, sometimes you used factor labeling to actually solve things. We're going to use equations to do our solving, and we're going to use something like factor labeling to just convert. And actually, when I was in high school and in college, we just called it unit conversions. It didn't really have a name like factor labeling or even dimensional analysis. It was just converting the units. And so I do have my answers out here for a couple of my problems, but we can still walk through them together. And so in this first one, I'm starting with 4 kilograms and I'm converting to grams. So I always start with what I know first. I make sure that my unit that I'm on my way to converting to is catty corner to the other one. Kitty corner or catty corner? Which do you prefer? And then I multiply across. So I know that in 1 kilogram, there's 1,000 grams. And I want to know how many grams are in 4 kilograms. And so I multiply straight across and I get my new value of 4,000 grams. Samesies over here, and we're going to do the exact same thing, but now we have 2 sets of units to convert, miles per hour to meters per second. Ooh, it's a 2-stepper. So first things first, I'm going to focus on converting the distance into meters, hence why I have the little pinkish purplish marker color there. And so in 1 mile, I've stayed with my kitty cornerness. In 1 mile, there's 1,600 meters. So I've kind of set it up that way. So great, that gets me to meters, but I also need to be in seconds. And so I started with 1 hour here, and I had to pop over one section to do these time conversions. I know that if I stay with my catty corner kind of setup, 1 hour has 60 minutes in it. But wait, I want to get to seconds. So I'm going to pop over again and say, well, in 1 minute, there's 60 seconds. And then if I were to do the math here, I'd be canceling units out along the way. And I guess there's no harm in doing it right now. So miles cancel out, hours cancel out, minutes cancel out. And what I'm left with is meters over seconds. And then I just pop through and I do this math. So 55 times 1,600. And then on the bottom, and I should include times 1 times 1. And then on the bottom, I do 1 times 60 times 60. I divide those 2 sets of numbers and I get 24.44444 forever. Let's skip doing any example problems for now, because here's the thing. With our limited amount of time that we have together this semester, there's not going to be very many unit conversions that you expose yourself to along the way. Let's just do one for fun. I'm excited to do one. Let's convert 100 meters per second into miles per hour. So I start with what I know, 100 meters per second. And I set it up like that. And really, if I wanted to, I could even say 100 meters per 1 second. Well, let's first convert our meters to miles. So I'm going to use a new colored pen for that. I know that in 1 meter, let's go the other direction. Let's say there are 1,600 meters in 1 mile. Awesome. That's going to result in my conversion from meters to miles. Now I got to focus on those seconds because I do want to get into hours. So I have 1 second. I need to get to hours. Well, there's 60 seconds in 1 minute. And I know that there is 60 minutes in 1 hour. And hour is what I wanted to end up with. And so I'll just plug and chug that into my calculator really quickly. Now, I'm not going to plug it and chug it in my calculator right now, because if I leave my video recording screen, I lose this video forever. And that's lame. So we'll calculate that at the end. Or maybe you can calculate it really quickly by pausing this video. Let's glance at a couple of the other things we see on here. So again, we're going to use equations to do all of our math. The factor labeling, I know for some people that's how they did their calculations last year, but we're going to use actual equations to do our thinking and to guide our lessons and our learning along the way. And we're not only going to just use these equations to figure out the answers to questions, we can also use these equations to actually figure out the units. And I'll walk us through a little bit closer when we get to our first unit equation, or our first most basic equation. And then throughout the year, we can kind of almost prove some of these other units as we're going through. So these are just examples right here, this section C, of how we can use equations to figure out our math and figure out our units versus like just kind of plugging and chugging as we go through. All right, let's pop over to page 15. This is where we're going to be finishing up for the day. All right, and I'm going to, again, challenge you to really diversify your pens and get a few different colored pens or pencils or highlighters or whatever you really like to use, but let's get a lot of good colors going. So first of all, delta. You're going to see the delta used a lot in your physics classes. And not only do you see the delta used for a lot of things, but you're going to have to understand what it means. And so something just like time. Whenever we're talking about time in our measurements, we are always talking about some quantity of time. So not so much like right now, but like how long did it take you to get to school? Okay, how long did it take you to run that 100-meter dash? All right, how long did you hold your breath? And all of those are maybe a change in time with some beginning measurement and some ending measurement. And yes, delta t, or I should say T1, is sometimes 0, but sometimes it's not. What if I have a person that's driving down the highway or driving down the Beltline for some portion of time, and I don't really care about their speed while they were on the highway or on Highway 14 or on Mineral Point. I care about what their speed is while they're on the Beltline. Now, their delta t will be the time that they enter the Beltline, whatever that is, to the time that they leave the Beltline, whatever time that is. And so that t value, those initial times and those final times, aren't necessarily going to be the total time that the object is moving. So you're going to have some type of start time. And that's T1. And then you're going to have some type of end time. Ooh, this is pretty easy. And that's T2. And to find the change in anything, any value you're talking about, you always go the second one minus the initial one. So T2 minus T1 gets us those time values. New pen. All right, well, we already start with two kind of unique and different words, but we're going to focus on position just to begin us off. So again, we're talking about a delta x. And so we're talking about some starting position and some final position. Starting position would be x1. Would be x2. And then again, to find that delta, or to find that change in position, that distance, that displacement, I go x2 minus x1. Now here's a big important note. Displacement and distance are different things. If I drive from my house to school and then I decide to drive back to my house, technically my starting position and my ending position are the same thing. They're both my house. And so my displacement would technically be 0 in that situation. Well, no, we're not thinking about that. We're thinking about the distance. And so, yeah, my position and my ending position were the school. But what was the total distance I traveled? All the way to school. Maybe that's its own x1, x2, and then from school all the way to my house. That's its own x2, x1, and then I add those two values together. But don't worry, we're going to be functioning pretty much only in this distance situation right here. And most of the time, either our x1 or x2 is going to be some type of zero origin scenario, whether it be I'm dropping something down to the ground or I'm starting at the school and driving away. There's not going to be too many scenarios like I suggested with displacement. Pretty much only functioning in that distance measurement. Speed. Speed and velocity are very similar and also yet different. Now, sometimes physics folks, and even myself, will use them almost interchangeably, but they're not exactly the same thing. Speed is really a rate at which we can see a change in position. Can you guys hear my dog itching? Her dog collar's going crazy. Okay, which position changes? Now the key word there is rate. Anytime I'm talking about a rate, I'm talking about per unit of time. Per unit of time. So I got a really good rate on my car loan. Well, what I'm talking about is how much money do I have to pay per the amount of time I have the loan. Oh, I have a really good rate for my cell phone plan. Well, how much money do I have to pay per month? But we're going to focus more so on our rate being how much distance changes per unit of time. So suddenly we're talking about a velocity that's a lowercase v is a delta x over delta t. In those units, if I was going to put those in units form, well, distance is measured in meters and time is measured in seconds. And whoa, check it out. Those are the units for speed. Remember, rate always means in something over time. Now let's talk about how speed and velocity are different, because we might use them interchangeably while talking, but they are different values. So here's the thing. Velocity is going to include direction. Suddenly, direction really matters. And all of a sudden, am I driving east on the belt line or west on the belt line? Am I throwing that ball upward or am I letting that ball drop downward? Direction is going to matter, especially a little bit later when we're talking about stuff like forces. All of these directions are going to be important. And so speed and velocity, they really are exactly the same thing, except now we care about the direction. So I'm going to write down same as speed, same units, same equation. So this equation is the same. The units are the same. The only thing that's going to be different, and it's going to expose itself a little bit later in the unit, is the direction. Because I can say, hey, the speed limit on the belt line is 55 miles per hour. And, well, what speed were you going? I was just going 45 miles per hour. Or, hey, I need you to get on the belt line and I need you to drive. And the whole time you're driving, drive 55 miles per hour. But which direction? Am I going one way or the other? This is especially going to matter as we start talking about objects moving maybe in two directions, because maybe for a portion of time it's moving south and then suddenly it starts to move east at another rate. Average speed and average velocity. Well, you know, we're not going to use average speed and average velocity that frequently. It is good to know that when we're thinking about the average, what we're thinking about is the total time and the total distance. So when we're thinking about the averages here, That color's a little light. Green. So our velocity, or our average velocity, is going to be the total distance change in total distance divided by our change in total time. And so a good example would be like your drive to the Brewer game. The whole time you're driving to a Brewers game, you're not going on the belt line at 55 miles per hour the whole time. You're going to start off by maybe driving down University, which, has a speed limit of 25 miles per hour. And then you're going to get on the belt line, and then eventually you're going to get on the interstate. And so then you're going to speed up, and then eventually you're going to get close to Miller Park, which has a new name now. What is it? American Family Insurance Park? I'm going to need somebody to tell me. But anyways, and so you're going different speeds the whole time. Ultimately, though, you can say like, okay, well, you drove all the way to Milwaukee. That's our distance. How long did it take you to get there? Okay, that's our time. And then I can find the average speed along the way. We're not going to use this average speed thing like at all this year. It's just good for us to kind of have in our memory banks for later. Now that brings us to instantaneous velocity and instantaneous speed. That's where we're talking about this given moment. What is the speed? So I like to think about something like Usain Bolt. So if I want to talk about, so first I should say delta x divided by delta t at a specific moment. All right. So this is kind of like the speedometer in the car. And the example I like to think about is Usain Bolt. When Usain Bolt ran the 100-meter dash in the Olympics, his highest speed during that measurement, the speed that they actually clocked him at as his highest instantaneous speed, was 27.8 miles per hour. That's how it's written usually when you see it on road signs. But really what that comes down to is 12.43 meters per second if I convert it into my math physics units. And so he was clocked with like a little speedometer, like speed gun, radar gun, when he was running in the Olympics. And this was his top speed, but that was his instantaneous speed right at that moment. That's what we saw as his top speed. It wasn't an average like we see here because obviously, he started from zero. He sped up for a while. He probably had this moment which it was constant velocity. And then after he's done with the race, he slows down a little bit. But we can see his top speed right there. All right, well, we're done with notes between the two videos. Hopefully you got some good stuff written down, and this will help prepare you for our speed lab. Now for the speed lab, the big thing that you're going to be doing is, and you're going to actually be utilizing this equation right here. You're going to be measuring different objects at different distances, and you're going to time them to get a time value. Now, hopefully, if you were lucky, you got a tape measure when you picked up your materials for school. If you didn't get like a little papery tape measure, maybe you could look around your home and see if you've got even just a ruler or a tape measure of some kind. If you don't have anything in your house that can measure, let's get creative. What can you use? Can you use your shoe length? I bet you could Google on the internet like size 10 shoe in inches or size 7 shoe in meters. And you can use that to get your measurements for your distance. If you need help getting a little creative with that type of stuff, you should stop into my ASR tomorrow, Tuesday, to get those values or to get a little bit of inspiration for how to do that one together. All right, we're done. Have a great night.